Okay, shall we get started? Okay, good. Is this lighting okay? You can see, perfect. Okay, nobody objects. And my voice is okay? Is it too loud? No? Okay, if it gets too loud, let me know. Sometimes it's hard to adjust. Okay, so I guess since you didn't quit yet, you're interested in this. That's good. Basically, I'm going to continue what we started last time. I'm going to give you one more example of how breaking the abstraction layers could enable you to get rid of a lot of overhead in the system. And I'm going to pick the example of memory refresh this time. And then we're going to do some course logistics, and then we're going to start some memory systems in terms of trends and fundamentals and some problems that we have in the memory system. Because as I mentioned yesterday, memory system is very important, and you will see its importance a lot more going into the first part of the lectures. But let's start with one case study of memory refresh. This is actually a fascinating topic for me. It's interesting that, well, human memory needs refresh, right? You don't remember, if you don't get reinforced, if you don't replenish something, things you may get lost. And we don't know exactly how the mechanisms are working in human memory, but we know more, of course, how computer memory works. I think there are analogies between human memory and computer memory, although it's not clear how far we can take the analogies, because I think we need to understand the human memories better. And I think a fascinating research area is understanding human memories and somehow bridging the gap between computer memories, or getting the best of both worlds, right? Because computer memory is good at some things but terrible at some other things, and human memory is also that way. Is there a way to reconcile this gap and get the best of both worlds? I don't know. I'm not going to tackle that over here, but I'm going to tackle a problem that exists especially in DRAM memory, and also any charge-based memory. If a memory is charge-based, electrons escape, and once the electrons escape, you lose the data. If enough electrons escape that you don't have the value stored in it correctly, then you lose the data, and that's what refresh is all about. And if you think non-volatile memories don't have this problem, unfortunately they do have this problem also. Resistive memories also have this problem, which we may talk about. They don't lose charge in that case, but remember we talked about 3dx point yesterday, right? It was based on phase change memory, and you store data in terms of resistance levels. But it turns out if you don't do anything to the memory cell, over time resistance drifts, meaning your resistance value changes slowly. Which means that if you cross a threshold that determines what's a 1 and what's a 0 in the resistance levels, then you may actually think something is a 0. In fact, you may have written a 1 over there. Basically, you lose enough resistance, you lose the data. So it's very fundamental. That's why I wanted to discuss also, even though the example that I'm going to give you will be from DRAM, which is a charge-based memory. Of course, DRAM should not be taken lightly, because DRAM is everywhere. It was invented in 1965 by Bob Denard, who's also famous for Denard scaling, which we may talk about later on. And it's been the dominant technology for main memory for like 54 years, let's say, and counting. Although that may change with the picture that I showed you yesterday with 3dx point, right? Things are, there are competitor technologies that are coming up. Okay, so let's talk about memory refresh. So just to refresh your memory, this is what we discussed. So your memory needs refresh also, as you can see. This is what we discussed at the late part of yesterday, and this is probably going to be one of your assignments in the homework for the review. So keep that in mind. I still like this paper a lot. It's a different way of thinking, I think, of multi-core systems. And this is what I concluded with last time, right? Basically breaking the abstraction layers and knowing what's underneath enables you to understand and solve problems and make a big difference. And I think of refresh the same way. That's another example. That's what I mentioned. Basically, if you look at DRAM in the system, it's this thing over here. Everybody has DRAM. All of these computers have DRAM. And if you go underneath the abstraction levels, remember I showed you the two-dimensional bank picture. If you actually look at each individual cell of that two-dimensional bank, you will see something that looks like this. Basically, it's a DRAM cell. Has anyone seen this before? A dynamic random access memory cell? Okay, I see more hands than I expected, actually. That's good. Because normally this is not covered in a lot of lectures. If you've taken a traditional computer architecture course, people don't touch it normally. If you're taking a microelectronics course, then you would have seen this for sure. But the traditional computer architecture course, unfortunately, doesn't touch it, even though it's one of the biggest bottlenecks that we have in the system today. Okay, but this is a DRAM cell. If you look at this, it consists of, so any memory device, we're going to talk a lot about memory, so I can introduce some of the concepts over here also while we talk about this. Any memory device needs two things. It has a storage component. In DRAM, it's this capacitor. This capacitor stores charge. And it also needs to have an access component. It's this access, or it's called an access device. In DRAM, it's this access transistor, the bit line and the word line and the sense amplification structure that you have over here. You don't need to worry about that right now. We'll go into more detail. Basically, for any memory to work, both of these components need to work reliably. You cannot just have a storage component and have no mechanism to access it. It makes no sense. And as I mentioned yesterday, in phase change memory, storage component was very reliable for decades and decades, but we didn't know how to construct an access component to it until very recently. That's why phase change memory has become very, very interesting, because people have put a lot of effort into constructing that access component. We'll talk about phase change memory later if we get to it in this lecture, but if not, later. So DRAM works by storing charge inside this capacitor, and I already say this over here. Clearly, if this charge is below some threshold, you can encode it as a 0. If it charge is above some threshold, you can encode it as a 1. Right? So there's a threshold that determines what's a 0 and what's a 1. And the way you read it is by enabling this access transistor, by applying some voltage such that this transistor is enabled, and then the charge perturbs the bit line, and you sense the change in the bit line. There's a sense amplification structure that senses whether this charge is above that threshold or below that threshold. If this charge is close to 0, then it causes a perturbation that drives the bit line down, and this sense amplifier, which is not shown here, amplifies that to 0. If this charge is above that threshold, closer to VDD, let's say, highest power, then it perturbs the bit line such that it goes up, and then the sense amplifier understands that this is really charged, and it amplifies that signal to VDD, and as a result you read a 1. Right? That's the idea. That's how DRAM basically operates. Of course, we could go into another abstraction level, but we don't need that at this point. If you need another abstraction level as to exactly how this works, you take the microelectronics design course that goes into how these charge curves work in DRAM and how this charge sharing exactly happens. We may cover some of that later on. Okay, so hopefully that's clear. That's the basics of DRAM. A DRAM cell. What else should I say over here? Okay, I guess I don't need to say anything. But basically, a DRAM chip consists of many of rows of such cells. So if you look over here, I'm showing you a single row. Well, actually it spans. A single row can be 8 kilobytes, let's say. And you can see that there's a word line, there's a row enable. And remember the picture that I showed you with the bank? When you activate a bank, you actually apply high voltage to this word line, which means that it enables all of the DRAM cells or access transistors that are connected to the word line, which means that all of the capacitors share charge with the corresponding bit lines and perturb the bit lines, and you sense all of those 8 kilobytes concurrently at the same time. So you have 8 kilobyte sense amplifiers over there, down there. And that's one row. And then you have columns, which I don't show over here. Clearly in the columns, you can have another word line over here, and another cell, another row of cells. And you can see that you can have tens of thousands of rows of such cells in DRAM. That's how you get large capacity. Okay? Okay, so we're going to deal a lot more with the structure later on. Because actually, if you look at any memory, it looks kind of like this. You have rows, you have columns. In fact, if you abstract things a little bit, phase change memory looks like this also, except you replace this DRAM with some other cell. It doesn't always work that way, of course, but that's the abstraction that I would like to have in your mind right now. Okay. So one of the problems with DRAM is it's called dynamic random access memory. It's dynamic. So this capacitor leaks over time. So if you go back over here, there's this capacitor. It has some charge or it has no charge. Let's assume it has some charge. Basically, it's there because this is not a perfect isolation that you have in the transistor. If the transistor is not turned on, you're not supposed to leak this charge, but nothing is perfect in the world, and this is not perfect also. which means that this capacitor leaks little by little over time to the bit line. Not enough to perturb the bit line, but it loses charge basically. And that's essentially called charge leakage in DRAM. And the memory controller, so of course, if you leak enough, then you lose the data. And this is a fundamental reliability problem with this technology, DRAM. If you leak enough, you lose data, you have a data retention problem. Which means that if you want to keep the data that you've written to these cells, you have to have a mechanism to restore the data once in a while. And this is called DRAM refresh. Basically, you need to refresh each row periodically to restore its charge. Okay, and let's take a look at some examples. Basically, well, how does refresh work? At an abstraction level, you need to activate each row every some number of milliseconds. Typical N is every 64 milliseconds. So every 64 milliseconds, you activate every row in DRAM. We're going to look at the consequence of this in a little bit. Actually, today things are going down. Today in many mobile DRAM chips, LPDDR chips for example, that's employed in a lot of mobile phones, it's already gone down to every 32 milliseconds. And also this is temperature dependent. At high temperatures, it turns out charge leakage is much faster. As a result, you need to refresh more frequently. At low temperatures, charge leakage is much slower because electron mobility is much lower at low temperatures. As a result, you need to refresh less frequently. So you can refresh less frequently. There's no harm in refreshing more frequently, clearly, right, in terms of reliability. You could keep refreshing more frequently than needed, and you keep the data reliable. Of course, the downside is you're wasting energy and wasting performance. Okay, so there are a bunch of downsides refresh. One is energy consumption. Clearly, you don't, if the technology was perfect, you store data to it and you don't need to replenish it. You don't need to refresh it, right? But now we need to refresh it, and each refresh really consumes energy. You need to activate a row, and then you need to activate another row. To be able to activate another row, you need to pre-charge the previous array, actually. That's how DRAM works, if you remember the explanation that I gave yesterday in terms of a bank operation. So each refresh actually consumes significant amount of energy. It also leads to performance degradation because whenever you're doing a refresh on a DRAM bank, the structure that we showed yesterday, you cannot access it. And that's a problem, right? If you're doing a lot of refreshes, and let's assume that a bank has 32,000 rows, which is very realistic. Assume that you're refreshing all of the rows in a single bank, 32,000 rows, which is not a good idea. We will talk about that later, perhaps. Then you're actually denying service to all of the requests that need data from that bank at that point in time. So this is actually a quality of service problem in addition to performance degradation problem. Basically, you may have some long pause times if you do refresh that way. If you schedule all of the refreshes such that you do 32,000 rows in a single bank consecutively. You can do the calculations, right? If each refresh takes, let's say 50 nanoseconds, which is optimistic, and you do 32,000 rows, now do the calculation and you figure out how bad it is. Now, of course, I'm exaggerating. There are a lot of tricks you can play internally in the circuitry. You can parallelize a bunch of refreshes. So you can reduce it by playing a lot of circuit level tricks, but still it's a lot of time. Okay, and it turns out refresh rate actually limits DRAM capacity scaling. If you want to increase the capacity of DRAM, there are two ways of doing it. One is you add more rows, which clearly increases how much more refreshes you do because you have more rows to refresh now. And the second thing you can do is reduce the size of the cells. If you reduce the size of the cells, that's good. You can have more cells per bit, per area. But as you reduce the size of the cells, it turns out the data retention becomes a bigger problem. A smaller capacitor has less charge, which fundamentally means that it's going to leak that smaller amount of charge quickly, more quickly than if it were bigger. That's the idea. So both of the ways of increasing DRAM capacity lead to increasing the refresh problem. You need to refresh more. And that's essentially why when I created this slide it was 64 milliseconds, but now it's 32 milliseconds. The refresh interval. Okay, so let me give you some analysis first before we actually move on. So hopefully the refresh is very clear. Let's imagine a little bit. Imagine a system with 8 exabytes of DRAM, which we're not that far away from actually. If you look at the supercomputers today, they have petabytes and petabytes of DRAM, and exabytes is not just an order of magnitude after that, right? We're not that far. So imagine this system, that's 2 to the 63 bytes. Assume a row size of 8 kilobytes, as I said, that's 2 to the 13. How many rows are there? Hopefully this is a very simple question, right? You divide the top number with the bottom number. That's 2 to the 50. I already gave you the answer of that. How many refreshes happen in 64 milliseconds? Essentially 2 to the 50. Basically, you need to refresh every row every 64 milliseconds, meaning that you need to do 2 to the 50 refreshes within 64 milliseconds in the entire system. Okay, these are easy questions, of course. The harder one is this one. What is the total power consumed for DRAM refresh? Essentially, it's not that hard actually, but you need to figure out the number. Basically, you have 2 to the 50 refreshes. You need to figure out how many watts do you need to spend for each refresh. And you multiply those two numbers, and you get a big number. I'm not going to tell you that big number because this is an exercise for you. Actually, you can find the answer probably in my digital circuits class if you've taken it. You may have done this exercise already. Okay, and then what's the total energy consumption of DRAM refresh during a day? Of course, if you know your basic physics well, energy is power integrated over time. Essentially, you multiply this power with time, right? That's the energy consumption. Of course, it's a good exercise to do this, and you'll see that the numbers are pretty large. But I'm not going to do that exercise for you. It's simple, but I think it's very instructive. And you'll get brownie points from me if you do it. Maybe real brownies also. Okay. And also think about the fact that this may actually become worse if basically this becomes 32 milliseconds, this essentially doubles, right? If it becomes 16 milliseconds, it doubles it doubles once more. So at high temperatures, actually, some of the refresh rates are today at 60 every 16 milliseconds. So at high temperatures, this also becomes worse. Okay, and if you want to increase the DRAM capacity going into the future, these will increase. So the number of rows will increase also. Okay, so we did some studies. This is early studies that we've done in this area. This is a paper that was published in 2012. I'm going to cover this actually in a bit of detail because I think this paper has a lot of interesting aspects for multiple reasons, as you will see. But this is one of the projections that we had done at that time. And this picture shows the device capacity that we have. This is the size of a DRAM chip, single DRAM chip, 2 gigabits, let's say. And we wanted to see what fraction of the time the chip needs to spend refreshing in terms of a function of the device capacity. So doing the study is not that easy because you need to make some assumptions, you need to also look at historical data, and you need to basically project into the future. And always these projections may or may not be perfectly correct, right? Again, we're architects, we're looking into the future this way. This is a perfect example of examining the past. Of course, there's a lot more that goes into examining the past than just these graphs. There you need to understand how the refresh current is scaling. You need to understand what's the refresh interval, how the number of rows is scaling, how the size of a DRAM cell affects the refresh rate. So you need to really model that at some level. And I'm not claiming that this is the perfect model. Actually, I believe this is today a bit exaggerated because things are changing, because people are reacting to refresh. So if you do this projection today, you will not get this number. But if you do this projection in 2011, you would get a number that looks like this. Okay, so if you do those projections, this is basically data from real devices. About 8% of the time of a 4 gigabit DRAM chip is spent on refreshing. You can think of this as you need to refresh the device for 8% of the time. You cannot access it during that time, right? Meaning that 8% of the throughput of the device is lost to refresh. That's another way of looking at it. Okay, assuming that the projections are correct and they look this way, we found out that, or we expected that 64 gigabit device would spend 46% of its time refreshing. That's a bit scary, I think, because you built this device and you want that to be operational. Ideally, you want that to be efficient all the time, providing data to you, but 46% of the time it's not providing data to you. Basically, 46% of the throughput is lost. Okay, so this is one downside of refresh. You get throughput loss. Okay, there's also energy. Energy is a bit harder. Energy is always harder than performance because there is a lot more involved in energy. And especially if you want to do scaling studies that look like this, you need to have even more assumptions. Basically, you need to do what I just described, do the modeling. But also you need to have some assumption in terms of what fraction of the, how often do you access DRAM. For example, I'll give you an example. Right now, I'm not touching my phone. The DRAM is in self-refresh mode. Meaning that the only thing it's doing is refreshing itself because there's no one accessing it, hopefully. unless some hacker put something over there, right? There's no one accessing the DRAM, but it needs to retain the data. It needs to keep active for many reasons. Taking phone calls is one reason. It needs to retain the data, meaning that it needs to refresh. But if I ask you the question, what fraction of the total DRAM energy is spent on refresh, what would you say at this point? 100, yes, assuming there's nothing else, that's right. Absolutely, but there's also some other leakage that goes on in the peripheral structure that are not due to refresh, so it's basically most of the energy is spent on refresh. But if I actually start doing something and if things start getting accessed, a smaller fraction of the energy is spent on refresh because you're actually accessing DRAM at that point. So actually if you're accessing DRAM continuously, refresh becomes a smaller fraction of the energy. So how much energy is spent for refresh depends on the usage pattern of your memory also. So keep that in mind. That's actually very much true in many cases. The previous one was a really maximum throughput loss kind of a study, right? This doesn't depend on the access pattern. This is the maximum throughput loss that you would get if you needed to keep data intact. Here you need to assume some things about how often are you accessing DRAM. How often are you accessing DRAM? So there's some assumption that goes into these numbers, but the assumption is not that DRAM is idle. So there's some accesses that are happening. So if the DRAM is idle, this curve is actually much worse. Okay, so if you make those assumptions with a 4 gigabit device, 15% of the DRAM energy is spent on refresh, which is still significant, right? You have some energy that you have in your system. Some of them goes to DRAM. Actually, later I will show you numbers from real systems that show that more than 40% of the entire system power goes into DRAM. So if you do 40% and if you do 15% of it, that's 6% of the entire system power, right? Which is a lot. We want to get rid of as much power as possible, and this is really just to retain data. You're not even doing useful work. Okay, so if you do the projections again, you see that a 64 gigabit device spends 47% of the DRAM energy on refresh. Again, this is not very good. You're spending almost half of your DRAM energy on refresh. Okay, so that's why DRAM refresh was a good area to study, and this paper actually created a lot of churn, enabling a lot of work in refresh, as I will show some of you, I will show some of that in a little bit. Okay, then of course the question is, how do you solve the problem, right? Clearly, we want these large devices because larger capacity is good. You can fit many more workloads and bigger workloads. We can fit bigger machine learning models, for example. Large DRAM is good for them also. That's one example. If somebody questions why do you need a bigger memory, you can always give the example of machine learning today, because the hindsight is 2020 right now. But there's a lot more other stuff, of course, right? Larger memories are usually good. Of course, we don't want that large memory to be wasting a lot of energy and also wasting a lot of performance. So how do we solve that problem? That's essentially where we started. So okay, maybe I'll start. Any ideas so far? I didn't give you a lot of clue on how to solve the problem clearly, so you may not have ideas. I'll cover one idea in a little bit. Yes?
Maybe you can alleviate the problem a bit by not refreshing the cells which were recently accessed.
That's a good idea, yeah. Basically, if you're recently accessed, which means that you replenish the data, because an access means you already activated it, then maybe ignore the refreshes that go into that. So how would you implement that?
Yeah, I'm not sure.
Yeah, exactly. I think that's the difficulty there. You need to basically keep track of which cells are recently accessed, which introduces some overhead, and you need to eliminate the refreshes. And then the question is, of course, to keep track of those cells that are recently accessed, you need to introduce other structures that consume power, that may affect your performance. Hopefully they don't affect your performance if you put them in the right place, but they will definitely consume power. Then the question is that trade-off a good trade-off? And how many refreshes do you reduce that way?
Yeah, it doesn't solve the problem.
Yeah, exactly. But I think that's a good idea. That's a good idea direction. Actually, that's been proposed in many works, and in the work that I'm going to describe, we compare to it also. So that clearly doesn't solve the problem of this case, right? Idle. And when my phone is idle, I'm not accessing anything. So that essentially doesn't add any benefit in that case. Yes.
Can you parallelize the refresh somehow and refresh more of the memory at the same time?
Mm-hmm. So that's also a good solution, at least for the performance problem, right? Because if you refresh more at the same time, you get rid of refreshes quickly, and then the accesses can proceed, right? So, what is the downside?
Energy?
Exactly, yeah. You will consume more energy at the same time. Actually, the downside is more power than energy, because if you want to do many refreshes in parallel at the same time, you need to draw a lot more power at a given time. And you'll basically strain your power supply significantly. But it can be done if you actually supply more power. Ideally, you would like to refresh everything at the same time, but it's not very easy, right? So fundamentally, you're limited by your power, and also the fact that you cannot refresh. Actually, this is not exactly true, but with the abstraction level that I set over here, you cannot refresh more than one row at a time in a single bank. That's not true. People play a lot of tricks, actually. They refresh more than one row at a time today. It's amazing how you look at the engineering of a DRAM chip. Inside, you can refresh many more rows at a time. So the solution you have is actually employed. But of course, not to the extreme extent where you can parallelize as much as possible. Okay, another one.
We don't need a full access to refresh the cells. Maybe we can reduce the power needed per refresh.
Okay.
I'm sure many engineering hours have been spent on this problem already.
I see. Yeah. No, that's so why do you think you don't need a full access to refresh?
I don't know. Maybe you don't lose all the charge during 64 milliseconds, but mostly just a bit, and so maybe you don't need that much energy to refresh.
Exactly. So that's actually a good point. Basically, exactly. How much? In the end, it depends on how much charge you've lost. If you lost all the charge, you'll need to refresh it in full. But if you lost, let's say, I don't know, 20% of your charge, then you refresh it with a bit less. So you don't need to drive the circuitry fully. So what's the downside of that?
You need to determine how much you've lost.
Exactly. Basically, you need to determine how much you lost, and it's not easy, I think. And it's similar to. It's actually a bit worse than determining whether you've accessed something, because it's a finer granularity information, and you need to do it correctly, of course. But I think these ideas are actually proposed in various forms, as you've guessed. Some of them are not as easy to implement. As you will see, this idea is also not easy to implement that I'm going to describe over here. But these are all very good ideas. I like the brainstorming here. Any other ideas? Maybe we'll solve the refresh problem and we'll be done once and for all. It's a very fundamental problem, so I don't expect a complete solution to it. Yes?
You can add a capacitor at the end of each row to serve as a timer. Like when you access a row, it's set to 1, and when charge became lower than a certain value, you refresh the row because there is leakage. So
I see. So you're basically proposing a mechanism that automatically refreshes, right? Yeah, I think that those sort of mechanisms, I mean, I haven't completely examined your mechanism, but those sort of mechanisms are certainly possible. But as you said, you need to add something to it, right? Yeah, there's always a trade-off, as you can see, right? All of these solutions are introducing some other trade-off. Yes?
Maybe you could somehow use the leakage to refresh the other cells.
Okay, this I haven't heard before. So how would you do that?
Well, I've spent many hours researching.
Okay, let me know if you find a way of doing that. It's very... Yes?
So the refresh rate is temperature dependent. So maybe cooling the DRAM takes less energy than refreshing more often, so you'd spend more energy refreshing, but then in the end spend less energy because you don't have to refresh.
You don't have to. Okay, I think that's an out-of-the-box idea, although I'm not sure if that trade-off works that way, because cooling also requires a lot of power, right, and a lot of infrastructure that you need to add externally. But if for some reason you need to operate at cool temperatures, at low temperatures, then certainly you can reduce the refresh rate. Any other thoughts? Yes?
Is the refresh rate a constant? So if we say that if we have to refresh every 64 milliseconds, does that stay constant or can we adapt that so that, like he said, that if the temperature increases, we increase the refresh rate, and if it decreases, then we need to refresh less often?
Yeah.
Something like that.
So it's not a constant. It's basically determined by the memory controller. But what you said is already done. It's basically we do a temperature-dependent refresh today. So if you're operating DRAM at high temperatures, then the refresh rate is actually 32 milliseconds in the technology that I described. If you're operating at low temperatures, then it's 64 milliseconds. And in fact, that granularity has also become finer over the years. Today we have a lot more finer granularity refresh in DRAM. So it's not constant today. But it's not constant based on temperature. Yes?
Maybe just add more error correcting codes.
Okay.
So just refresh them more often, the error correcting codes, to recover the ones you've lost, and then the normal bits you just refresh less often.
Okay, what do you mean normal bits?
So the non-error correcting bits.
Okay, I see.
So you keep the error correcting bits safe and the other ones
I see.
refresh
Okay.
less often.
Okay, I think that's also interesting. I mean, there's certainly a trade-off between error correction and refresh, right? If you, of course, error correction comes at a cost, right? You need to add some redundancy so that you store redundant bits so that you can recover the old data. But yeah, I see these as kind of two extremes. You can have extremely strong error correcting codes and no refresh, and you can have a lot of refresh and no error correcting codes. And clearly, there's a trade-off space in between. The question is, how do you actually find that trade? I think you had another idea that's a little bit different in the sense that you treat the error correcting codes a little bit differently and refresh them more often, and maybe refresh this other part less often. I think these are definitely interesting ideas. But of course, clearly, whether or not that idea makes sense, or any other idea that we've discussed makes sense, requires a thorough trade-off analysis in terms of how much that would affect performance, energy, quality of service. And we will do that in this work that I'm going to describe. But not for that particular idea. Okay, any other ideas? Thoughts? This is good. I like this brainstorming. And by this way, I think you're also seeing how a computer architect operates, right? First of all, I've identified the problem for you. That identification of problem is really, really important also in computer architecture. Basically, you look back and you look forward, and you try to identify what's going to come in the future so that you don't hit that problem as much. And then the next step is, of course, how do you solve the problem? So let me give you what we have thought about in solving the problem at that time. So basically, the observation is that all DRAM rows are refreshed every 64 milliseconds. That's at least in some temperature level, right? So the key question is, at least the critical thinking that we started out with was, do we need to refresh all rows every 64 milliseconds? And if you ask that question, then the next step is trying to answer that question. What if you knew what happened underneath in the DRAM cells and exposed that information to the upper layers? Meaning, maybe these DRAM cells have different data retention properties. Some of them can retain data for much longer. Some of them can retain data for much shorter. And maybe you'd have heterogeneous refresh rates. So that's essentially what happens. If you look at examine what's underneath, you look at the retention time profile of different DRAM cells. Today we're treating everything equal, right? Everything needs to be refreshed every 64 milliseconds. But now let's take a look at how much each cell can retain data for. It looks very heterogeneous. Basically, this is one sort of binning, of course. So these cells can retain data for this amount of time. These cells can retain data for this amount of time. And everything else can retain data for something over 256 milliseconds. Of course, you can go even more finer grained and look at, 10 seconds, 100 seconds. Does that make sense? So basically, if you look at this picture, you see a lot of heterogeneity. That's the first thing. And the second thing is, most of the cells don't need to be refreshed every 64 milliseconds, right? Actually, we're refreshing DRAM every 64 milliseconds because these cells cannot retain data if you refresh it at every 128 milliseconds, for example. So once you see a picture like this, you can ask the question, you can ask many questions, but one of them is, why do you have such a profile? Any guesses? Why do we have such a profile in the device?
Many manufacturing impurities and effects.
Exactly. Nothing is perfect, if you remember, and manufacturing is not perfect also. So not all DRAM cells are exactly the same. Some are more leaky than others. And this is manufacturing process variation. Why are they more leaky than others? Well, some of them may have very small capacitors. There are multiple reasons for it actually. You may have a very small capacitor which can contain little amount of charge, and that leaks very quickly. Or you may have a leaky access transistor. The access transistor is weak, so charge leaks very quickly. Or you may have some other noise in the bit line that affects the charge to be drawn out relatively quickly, right? So there are multiple reasons over there, which we cannot get into right now, but those are examples, right? So if you want to understand this part and solve the problem at that level, you need to go down that level also and understand why this is the case, right? Okay. So there's a solution direction at the device level also. Maybe if you understand why this is the case, you try to create some transistors that are not leaky, but that's a very hard problem because you will always have process variation. You cannot create devices that are immune to process variation today. Okay, so basically we have an opportunity. How do we take advantage of this profile? Assume we know the retention time of each row exactly, and that's exactly what we assumed. We'll see if this is a good assumption or not later on. But assume that somebody gives you this profile. What can you do with this information? Any guesses? Yes?
Just recharge them as needed.
As needed. Basically, adapt the refresh rate to which cell you're considering to refresh at that point in time. Exactly. And that's the obvious thing. What else can you do? Yes?
You can just not use the ones with the really crappy.
Exactly, yeah. Really crappy retention times, right? Somehow map them out so that no one allocates them. That's a perfectly reasonable direction also. Because that's very small, right? Maybe you don't care. Of course, in the future, maybe they'll become larger and larger over time, so maybe that may or may not be the best solution. Okay, so and then the answer that you give to this question also probably should determine the answer of who do we expose this information to, right? For example, if your solution probably needs to expose the information to the memory controller, and the memory controller determines what needs to be refreshed, how often, but the other solution that was proposed in terms of mapping them out, probably the operating system needs to be involved in that, or at least some firmware needs to be involved in that so that they're mapped out. Okay, how much information do you expose? I don't want to get into that right now, but basically all of this affects the hardware and software overhead you have, power consumption, verification complexity, and cost. Again, this is a trade-off also. You need to do the trade-off analysis of whether or not the idea that you have over here is good. By the way, any other answers to this? Yes?
Maybe we have unimportant data, like some cache data or something, and we put this in the less reliable cells, and we don't care if they get corrupted. So we just don't use the data anymore if it gets corrupted.
Okay, I see. I like that idea. Basically, somehow understand the characteristics of your data and place the things that can tolerate errors to those cells that are weak, essentially, and increase the refresh interval. But then you may still need to detect the errors in cases where you really care a little bit about the reliability, right? Yes?
Just hash. Store the hash in the safe area. And
I see.
Yeah.
Okay, I see. Basically, you're proposing an error correction mechanism, sure. Okay?
I have a clarification. Can we differentiate between a capacitor that has leaked out of charge versus a capacitor that's storing like zero charge for data?
I mean, it's not easy. Basically, you need to develop a circuit mechanism, which one of you somehow was trying to propose, and that comes at an overhead. Basically, it's certainly possible to detect things like that, but it comes at a very high overhead in general. Yes.
Maybe you reliably know that some application is going to use X data frequently. Maybe operating system knows this. It can schedule that application uses the data which needs to be refreshed frequently, so it's going to be refreshed by X.
Yeah, exactly. This is building on the previous idea, basically. Somehow, but then you don't have the overhead of keeping track of what is accessed or not, right? You basically somehow magically know. Of course, now you're relying on some guess. If that guess is incorrect, what do you do?
Well, operating system might have information that an application which has been running for a while uses the data frequently, and maybe then you can like steer the application to use this data frequently, and then you
I see.
just access it frequently.
What if the application stops accessing some data frequently?
All that have to be like kept track of.
Exactly. So you still need to keep track of something. And that usually adds overhead. But I like the thinking direction, basically. Somehow mapping the data that's frequently used to those cells that need to be refreshed frequently, and then getting rid of refresh in those cells. Any other ideas? So now you can see how rich this is, right? We're just talking about a single problem. It's a very important problem, but it's very rich in terms of potential solution directions. Yes?
I mean, one application that we're pretty sure that will often access that part is the page buffer of the OS.
Mm-hmm.
We just would map the page buffer there, and yeah.
Exactly. Yeah, I agree. I mean, you can find these structures that are often accessed, but usually the problem with those solutions is, when your assumption goes wrong, you lose the data. And there are cases where your page buffer is not accessed that often also. So you need to be very careful. But we're going to talk about some work that actually has that idea also later on, basically somehow. Anyway, I don't want to go into that right now. Okay, so and then the next question is, of course, we kind of assumed this profile exists and we know it. How do you determine it, right? That's another question. And we're going to talk about this because this assumption is actually a very strong assumption. It's very hard to know this profile perfectly, it turns out. So everything we've discussed may be useless in a sense, but that's not true. Okay, but this is the beauty of being a computer architect. You can dream. Your dreams may not be perfectly realizable at this point in time, but if you solve some steps, your dreams may become realizable, basically. And I think of this as that way, basically. Creativity is that way, right? You dream something and you have a solution. Maybe it doesn't work at this point in time, but you work towards making that solution work. And I think all of you have some solutions, and you can work towards making all of those solutions work. You may hit some bottlenecks at some point with some of the solutions, so it's good to understand what bottlenecks you may hit early on, as opposed to later on. Because you don't want to spend 10 years of time developing a solution and only to figure out that it's not going to work, right? Okay, basically I think we've discussed a bunch of solutions over here, and it's really spanning across the things over here. We could discuss a lot of things related to the operating system, but I think there are other things that are related to the program and language. If your compiler, for example, can do analysis of how frequently you're accessing the data, it's also possible to apply a solution like what was proposed. Maybe the compiler maps the frequently accessed data, or hints that this data is frequently accessed, and later on somebody had mapped the data. Maybe the programmer knows that information, right? Of course, relying on all this information you need to be very, very careful, clearly. And if you have algorithmic information, maybe you can do even better, of course. But then at the algorithm level, time is different, right? You still need to understand how the algorithm translates into execution time in terms of milliseconds in this case, because you're really dealing with milliseconds. Okay, and maybe there are some other device level solutions which some of you were proposing as well. Okay, so let's take a look at this picture a little bit. Essentially, the observation is that an overwhelming majority of DRAM rows can be refreshed much less often without losing data. For example, this is a picture that we took from a Samsung paper. Samsung published this paper in Electron Device Letters, where they showed this kind of picture, basically. We replotted, of course, based on the data that they have. But this is refresh interval on the x-axis, and this is the cumulative cell failure probability that you get. And clearly, at a refresh interval of 64 milliseconds, you don't operate. This is not an allowable operation point. And this is the cell failure probability you get. And if you increase the refresh interval, you'll get more failures, clearly, as expected, right? And the curve looks like this based on the data that was generated by folks at Samsung. And this is another axis that basically translates this cumulative failure probability to the number of cells in a 32 gigabyte DRAM system. And you can see that this is 10 to the 0, this is 10 to the 2, 10 to the 3. So basically, if you look at this point, 256 milliseconds, only approximately 1,000 cells need to be refreshed every 64 milliseconds. So you can see that as you climb this curve, the number of cells increases exponentially, right? That's how the axis is constructed over here. Okay, that sounds good, right? basically we still have a very small number of cells. That picture is actually constructed based on this graph over here. Now, of course, another question is, where are these cells? It turns out these cells are randomly distributed. This is a random process variation. These 1,000 cells, you can pretty much be sure that it's 1,000 rows across the device. Okay, so can we exploit this to reduce refresh operations at low cost? And basically we're going to focus on that. I think I already said this. Only 1,000 rows in 32 GB DRAM need refresh every 256 milliseconds, but we refresh all rows every 64 milliseconds. And the key idea of the proposal is to refresh weak rows more frequently and all other rows less frequently, as you have also observed. So let's take a look at how we do it. Of course, now you have the idea. The idea is sound based on prior data. Now the question is how you'd actually go about doing it. You need to keep track. You need to first of all identify which rows are weak, which rows are strong. I'm going to assume that again. But then even after you identify, you need to make sure it works right. So okay, the mechanism of radar actually consists of 3 steps. First of all, you somehow identify the retention time of all DRAM rows. This can be done at design time or during operation. So we're going to get back to this because this turns out to be the toughest part among the 3 parts. The second part is how do you store these rows? Basically, you need to store which rows need to be refreshed at what frequency, right? And that storage needs to be somewhere. And it's, the proposal here is that it's in the memory controller. Now, how do you do that storage? If you do not do it carefully, this could lead to a lot of overheads, right? So for each row, let's say you have 3 different refresh intervals. It should be refreshed every 64 milliseconds. Or 256 milliseconds, or 128 milliseconds, or 256 milliseconds. That's 3 different refresh intervals. And to be able to encode 3 different refresh intervals, you need 2 bits. So that you need at least 2 bits per row for that. Now the problem is 2 bits per row. If you have 2 to the 50 rows, that's a lot of rows. Well, 2 to the 50, I exaggerated, of course, but if you want to grow the size, even if you take, let's say, a 64 gigabyte DRAM, what is the 64 gigabytes? 2 to the 36, right? And 2 to the 13 is the row size, so you have 2 to the 23 rows. That's still a million, more than a million rows. Actually, it's 3 million rows times 2 bits. That's a lot of storage in your memory controller. And you need to have this somewhere in the memory controller. You can have it in the DRAM chip also, but there's a lot of other trade-offs that happens in the DRAM chip, which we will briefly discuss later on. So this paper actually tackled this problem. How do you actually store the retention time bin of a given row? And we use something called Bloom filters. Does anybody know about Bloom filters here? Only one? Okay, I see more people, somewhat. Maybe not fully confident if they know. Okay, I'll talk about Bloom filters because this is not really a specific structure for hardware, or again, this is a structure that is essentially that spans the hardware and the software. You can use it in software, you can use it in hardware. And these are data structures. All data structures are that way, but this is a particular data structure that's very good for hardware implementation. So basically, we need to somehow store in bins which rows need to be, the row addresses that need to be refreshed every 64 milliseconds, every 120 milliseconds, and that's enough actually. The rest, you don't need to store, right? So basically, if you want to keep track of this information, you need to have two data structures. One data structure that keeps track of the row addresses that need to be refreshed every 64 milliseconds, and another data structure that need to be refreshed every 128 milliseconds. So you've already reduced the cost a little bit. But we still don't want a lot of storage for this, because as the chip size grows, all of these also grow. Okay, so I'm going to talk to you about Bloom filters in a little bit. Basically, you can reduce the storage to 1.25 kilobytes for a 32 gigabyte DRAM memory, which is much better than what I just described. But you could also optimize what I just described, but we're not going to go into that. Okay, assume that this is also done. Now you have these data structures in your memory controller that tell you which rows, which addresses need to be refreshed at what frequency. Memory controller basically, whenever it needs to refresh a row, it keeps generating addresses basically to refresh. That's one way of implementing a refresh. You always increment the address that you want to refresh, and then you check, should this address be refreshed now, or should I wait until the next interval? And that's, the memory controller essentially consults these bins, the data structures that store these bins, to determine the refresh rate of a given row. That's the idea. And this is also easy to implement. It's not that hard. The hardest part is really here, This is also a hard part, and you need to be for hardware overhead. So let me give you the results first, because I think results are also good to look at because it's motivational. And when you get the results, you need to do simulation in this case because you don't have the hardware clearly. So you need to resort to simulation, which you will resort to in this class. You will do a lot of simulation. Maybe we'll simulate this one also, let's see. But the hardware cost is this, and refresh reduction is basically almost 75%. And you can guess that, right, based on the picture that I showed you. Most of the cells need to be, can be refreshed at 256 milliseconds. Essentially, for most of the cells, you reduce the refresh rate by 4x. But not all of the cells. And on top of that, there are some false positives in the Bloom filters, which we will discuss. So you need to refresh extra. As a result, this is almost 75%, which is a big reduction. And this leads to, according to the simulations, a dynamic DRAM energy reduction of 16%. If the DRAM is idle, you get even more power reduction. And performance improvement also is high. So this is an idea that improves both performance and energy. Why? Because refresh is consuming both of them, right? You're getting rid of this thing that consumes both. And this is also an interesting study to do whenever you're actually projecting into the future. Is this idea good enough for the future? And how good it is. So this is an example, for example. This is device capacity again in the picture I showed you. This is the baseline auto refresh scheme. You can read about it in the paper. And this is the radar scheme. As you can see, with a 4 gigabit device, the benefits are 16% over here. That's the baseline we assume. If you project into the future, the auto refresh scheme consumes a lot more energy per access. It's increasing this way. As you can see, it's exponential. Radar scheme is also increasing actually, but it's increasing much slowly. So at a 64 gigabit device, you're saving 50% energy per access. But ideally, if you want to scale something into the future, ideally you want this sort of overhead to be constant, or going down, of course. If it's going down, that's great. In this case, you want this green bars. If you're really truly solving the problem completely, you want these green bars to stay constant at the very least. But clearly it's not staying a constant, right? Even a solution like radar is not enough to keep scaling to go forever. So keep that in mind. That's why it's good to do these studies. This basically shows you, do I need another solution? I mean, of course, in this case, maybe we didn't optimize radar as much. Take that with a grain of salt. That's also possible, but it's very hard to optimize an idea for every single system, for every different parameter. Keep that in mind also. Whenever you read papers, that's why it's very important to be very receptive to the ideas. But the evaluation may not be done perfectly. In fact, I don't believe that there can be any perfect evaluation, because an idea is an idea that stands by itself. Somebody can take that idea and apply it in a completely different context and maybe get a lot better benefits in that particular context. So whenever you're reading papers, keep that in mind. There's an idea part and there's an evaluation part. And even though the authors do their best to do their evaluation, they may not always anticipate all possible uses of the idea clearly, right? I think it's just impossible to do that. Okay, if you look over here, this is also very interesting. This is basically performance in multi-core workloads. Actually, refresh becomes a bigger problem when you have many cores accessing main memory at the same time. Memory is a bottleneck. With a 4 gigabit device, you get 9% performance improvement. And with a 64 gigabit device, you get actually a lot more performance improvement over here. Part of this is because some workloads are getting unfairly denied service because of these refreshes that happen over here. It happens. Okay, so you can see that benefits increase as DRAM scales in density. Okay, so this could be another reading for your homework assignment. Is this interesting? You're willing to read it? Okay, so that's good. And if you're interested, there are further readings also, which we will talk about later on. This is another idea, basically parallelizing refreshes with accesses, but let's see. So the second takeaway, well, it's the same takeaway actually. What we've done right now is basically broken the abstraction layers. Somebody dictated that you should refresh everything 64 milliseconds. With critical thinking, we questioned that. Should we really do that? And we figured out that no, we shouldn't, because there is some real data that supports that you don't have to do it that way. And then you solve the problem, right? And this is a very good example of that. Of course, a problem is never completely solved. There's also another takeaway. Oh, I don't know why this is doing that. Basically, cooperation between multiple components and layers can enable more effective solutions and systems. Now, what does this mean? Basically, now the refresh is really, the job of the refresh is distributed across different components. Memory controller is doing something, and it's sending refreshes to DRAM, but somebody else is also identifying which rows need to be refreshed at what frequency. And some of the other ideas that you have developed actually disturb, let's say, in the good sense of the word disturb more components. Right? Operating system now needs to become aware of which rows have which retention times, right? So by actually breaking these layers, you can actually build much better systems in the end. So let's dig deeper though. So we are not done yet actually with the refresh. Actually, this may be a good time to take a break. What do you think? Okay, let's continue now. So hopefully you didn't forget what we discussed. So we were discussing radar. How do you make this work now? That's the question. But I think I'd like to before say something like this. Basically, good ideas are a dime a dozen, meaning that there are lots of good ideas that you can come up with, and you came up with lots of these good ideas. The real trick is really making them work. Oftentimes, that's the real contribution in the end. So keep that in mind. You will see this many times also for many other ideas also. Even though some idea may be really old, initially that's developed, that's a great idea, it may not be adopted because nobody has really made it work or proved that it could work. Okay, so let's take a look at Gradle again. This is the mechanism that we have, profiling, binning, and refreshing. Let's take a look at these different steps first. So you need to make all of these work, assuming that this is the idea that you have. So first of all, you need to make profiling work. I'm going to defer that again. Basically, this is what we said. You could actually profile a row. You write some data to the row, prevent it from being refreshed, and measure the time before data corruption. Right? We can look at an example that looks like this. Initially, you have this. After 64 milliseconds, you have this. After 128 milliseconds, you have some data corruption, as you can see. You can compare it to the old value. Of course, it's not that easy, right? You can build a circuit to do this. It's possible, but then you need to change DRAM. Now, how do you do it in real life? Basically, it's a profiling mechanism. You basically write the data and then read the data after 64 milliseconds. If it's intact, then you know that the row can store data for 64 milliseconds. But you're not done yet. How do you actually figure out if it can store data for 128 milliseconds? You cannot just keep it going. You need to do this process again, right? Because when you're reading it, you basically disturb the process. You basically refreshed it, right? So you do it again. You write the data and then after you read it after 128 milliseconds. In this case, this row lost data. So you can say it doesn't retain data for, so it needs to be refreshed every 64 milliseconds basically, right? Because it doesn't retain data for 128 milliseconds. So you need to put this row address into the 64 to 128 millisecond bin. But you can see that row 2 and row 3, they're fine. So you need to figure out basically how much each row can retain data. And if you have these 3 bins, then you need to do this profiling for every row 3 times. So you can see that this is also costly, right? Of course, this is one overhead of the profiling. Now the question also arises, who does this profiling? We'll get back to that later on. It becomes hairy when you think about who does this profiling. Assume that this is done, though. Is it really easy? Actually, maybe I shouldn't assume that it's done. Let's basically talk about profiling. Any guesses? Is it really this easy? This is the proposal. Yes?
I was wondering, once you've done the profiling once, is there a chance that like the DRAM cells get worse over time, so you actually have to do it like over and over again, so it's not like a one-time process, but you have to like put the overhead in several times.
Exactly. So that's one reason why this may not be that easy, because you do it once and then you do it later on. Do you need to do it later on? Because some DRAM cells may actually become weaker over time for whatever reason. They could age, for example, right? That's certainly a concern. And that's why it's not that easy. That's one of the reasons.
Also, perhaps when we put it, if operating system does this, it also has to stop doing other stuff in order to profile frequency or the memory management units.
That's right. So if you need to do it during online operation, there's some overhead, right? And there are good reasons to do it during online operation. So because can you trust this profile? But then once you start doing it during online operation, there's overhead that you incur because this profiling takes time, as you can see, right? You can imagine that this is actually a pretty long time. What else? Why is it not as easy as I described? Or if you think it's easy, you can also argue that position too. Yes?
They're probably not always going to fail after exactly 128 milliseconds.
Mm-hmm.
Sometimes they might not fail until later.
Okay. Why?
It's just kind of a little bit random, I guess.
Why?
There's a whole lot of other electrons going around.
Okay. I like that reasoning. Who knows what these other electrons are doing, right? No, I think you're right, basically. But there are reasons for it. Yes?
Well, the profiling you're doing is kind of like a snapshot taking at like one specific moment in time, or like over 64 milliseconds, but it might be that at a different temperature, things work out completely different, and then the profile that you created is no longer valid.
Exactly, yeah. So temperature is certainly a problem, actually. But the paper actually covers that. So essentially, you need to have different profiles for different temperature ranges. That's absolutely true, because clearly there's actually a very interesting exponential curve in terms of temperature. You lose charge exponentially as temperature increases. So you definitely need to take that into account. But temperature is actually a very well-known effect. That's the easier part. Yes?
So you need to restart, lose all the data on the chip before doing profiling, because if you want to do the profiling after some time, maybe to recheck if the cells have lost.
Exactly, yeah.
But you need to restart overwrite all the data there like once.
Exactly, yeah. That's a real issue, basically. You have some data in DRAM and you want to figure out how often that row that houses that data needs to be refreshed. You have to store that data somewhere else first, right? You cannot just do this on the data that you have over there, right? Yeah, that's a real overhead also. You need to move the data somewhere. Yes?
I'm thinking about if we are taking snapshot, we cannot read all the data at one same time because of the limited I/O.
Yeah, certainly. I mean, basically, you need to go through the I/O bus or memory bus to read this. So it adds overhead. It slows down the application. It adds energy overhead for sure. Yes. Okay. What else? Keep thinking critically. There are some things in the picture that you can question, for example. A lot of things, actually. You question some of them. I will get back to the random part, because the random part is actually the worst part. Yes?
Maybe the leakage is different for zeros becoming ones and ones becoming zeros.
Exactly, yeah. You can question, is this the pattern that you want to test? Basically, we've written all ones over here, and looking at whether they go to zeros. What if you've written only zeros? What if you've written a pattern that's very different, right? 1 0 1 0. So that's actually that's the other hairy problem here. It turns out this is not the best pattern. Zeros are not the best pattern. Also, you really need to create enough. Basically, the values you store affect how much charge there is across different capacitors, and how much noise, how much coupling these different capacitors have. This is called cross-coupling capacitance. And the charge leakage gets affected significantly based on this cross-coupling that happens between different capacitors. And that's the abstraction that we're going to stop at. Of course, you can go into how much modeling this capacitance, for example, but we're not going to do that. But this is actually the hair. This is called data pattern dependence. Essentially, refresh rate or retention time of a DRAM cell is dependent on the data pattern that's stored inside the cell and that's stored around the cells, in the cells that are around the cell. Now you need to find the worst data pattern that's possible to be able to find the worst case retention time of a given cell. How do you do that? It's not easy, actually. You can test with all data patterns, but of course that's hugely problematic, right? What is all data patterns, first of all? How far do you need to look in terms of the proximity of the cells? That's really infeasible, basically. So you really need to be smart about picking the data pattern. And the paper a later paper covers this. Not this paper, not the radar paper. Radar paper assumes that you can actually do get this profile information perfectly. Anything else? Yes?
Maybe how do you accurately measure time, and at what level do you want to do it? Maybe the hardware level or the software level?
Mm-hmm. Yeah, basically the 64 milliseconds versus 128 milliseconds. Yeah, I think that's a good point also. I think with this granularity, it's not a big problem. But if you want to go finer granularity, I think you'll have to do this in hardware. But yeah, software, if you try to do it in software, it's also possible, but now a lot of other things come into play in terms of that software should not get delayed, for example, for some other reason. But that's a good point. If you want to go finer granularity, I think that'll become even worse. What else? If there's anything else. I think we've hit the major points, although I still don't have a good answer for the randomness. You've hit a good point over there. I guess you don't have any good answer yet. I don't think anybody has a good answer to that, but we have a known process. Okay, so basically, I think we've answered this question. Is it really this easy? Not really, basically. And this is really the difficulty in the idea. So I think I've already discussed the two. This one I have discussed a little bit more. Basically, there are two big challenges, other than the challenges that you described, which are all challenges, but these are the two most difficult ones, I think. Like temperature, we can handle. Overheads, you need to somehow handle. We'll talk about that later, maybe. I'm not going to go a lot deeper into refresh today. This is just an example. So we'll have another lecture on DRAM reliability at some point, perhaps. We'll go deeper. But this one is a problem, and this one's the randomness problem. So let's take a look at, well, I guess I don't have the slides over here because we're going to cover some. Basically, this is a DRAM cell's retention time depends on the value stored in the cell and the cells around it. So you need to find the worst case data pattern to get the worst case retention time. And what is this worst case data pattern dependent on? This is really dependent on the structure of the DRAM. This is dependent on process variation. So it's actually not so easy. Even the DRAM manufacturer may not perfectly know, although they have a lot more information. And if you want to do this in the memory controller level without having information from the DRAM manufacturer, then it becomes even harder. And you will see in the paper that I'm going to talk about briefly that there are a lot of data patterns that are tested. So in the end, this boils down to testing DRAM with different data patterns. And it takes time, and you would like to minimize this time. But I think there are solutions to it. You can be smart about this, add some margins. This is the more difficult phenomenon. Let's talk about this one. This is called variable retention time. Essentially, this says that the retention time you measure at this point may be different from the retention time you measure later. And clearly vice versa. So you cannot have a single measurement that gives you the minimum retention time. So you need to measure many times. And it turns out this phenomenon is random. So this is one example. This is real data from a cell from some manufacturer E with a 2 gigabit chip family. And this is at room temperature. So you see that retention time is actually very high. It's in terms of seconds. At room temperature, this is a relatively, let's say, strong cell. It can retain data for seconds. And this is the time when we measured the retention time. So we basically measure the retention time of the cell repeatedly many times over an interval of 10 hours, let's say, 10 hours or so. And you see that it's not constant, right? There are cases where the retention time dips to 2 point something seconds, but there are cases where the retention time goes up to 6.1 seconds. In fact, 6.1 is the highest over here because we refresh at that interval in this case. Basically, it could actually have retention time much higher, but we didn't measure that. So you can see that this is a variable retention time phenomenon, right? So it's a bit sad. Meaning you need to find this early on. So if you found this, and if you test it for 2 hours, that's not enough, right? Because it's not 2.7, it may be more like 2.2 seconds, right? And this becomes worse actually at higher temperatures. The paper shows that data. At higher temperatures, it becomes more erratic. So why is this happening? Actually, this is, let's see. Okay, I didn't say this over here. We will have more detail over here. But this is happening because of the randomness. And the randomness happens, let's see, I don't have the DRAM cell picture. But let's go back to the DRAM cell picture. Remember, we're at slide 27. So if you go back to this DRAM cell picture, what happens is there's a random process that people have shown. This was actually discovered in 1987. It's called the variable retention time phenomenon. They basically found out that charge randomly gets trapped in this access transistor, and when that charge gets trapped in the access transistor becomes very leaky, and when it becomes very leaky, charge leaks out very quickly from the capacitor. So this is called trap-assistant gate-induced drain leakage. That's the scientific terminology, TAGIDL. And this happens essentially randomly as far as we know. It's a random memoryless process. So you cannot predict it, basically. And there's a time factor, of course, involved in the randomness in terms of how frequently this happens. Okay. And that's the reason why randomly your retention time can change. And as a result, you have the picture that looks like this. And the paper covers actually what's the time interval. So you can think of this as you have a high retention time state and you have some low retention. You care about the lowest retention time state, right? When do you encounter the lowest retention time state? That's what you want. That determines your testing time. And if you encounter that after 6 hours, that's a very long test that you need to do, right? And it turns out, unfortunately, you encounter that sometimes days later. So that's the difficulty of doing this test over time. But only by digging deeper you can find out this information, right? That's exactly how we found out this information. Now, of course, once you know this, then the question is, how do you deal with it? Okay, basically, what is the implication of this variable retention time on profiling mechanism? Profiling is basically figuring out the retention time, right? Basically, there are two problems. There doesn't seem to be a way of determining if a cell exhibits VRT. I call it VRT, without actually observing a cell exhibiting VRT. This basically says it's a random process. That's not predictable. And this is also shown in other cases. And we actually showed in the paper that I'm going to reference that this problem is getting much worse when you reduce the size of a DRAM cell. Because this random process, it's becoming more like quantum-like effects essentially. As you reduce the size, this becomes more erratic. Like, I think your explanation is kind of capturing it, right? There are a lot of electrons moving around somewhere and they're causing problems. Maybe not a lot of electrons, actually they're reducing in size, but they're becoming more erratic. And basically, there's another problem which is really interesting. You can say that, I don't care about this, let the DRAM manufacturers handle it, right? Well, that's not exactly true, but basically it complicates retention time profiling by DRAM manufacturers. What happens is, when you actually, essentially it turns out that if you expose memory chips to high temperatures, you can get variable retention time in cells that were not previously susceptible. So this is actually affected by how much temperature you're exposed to. So for example, when you're soldering and you're taking a DRAM chip and soldering to a board or a DIMM, you're exposing it to very high temperatures, like 300 degrees Celsius, for example. And that changes the retention time profile and variable retention time characteristics of the cell. So DRAM manufacturer may find out, doing a lot of testing, which is actually cost for them, which is not good, some variable retention time cells, they can say, oh, these are the cells that exhibit variable retention time, be careful about those. But their information is useless to you if you're going to take the DRAM chip and solder it. So you need to do something about it as a system manufacturer or system designer. So that's why the problem is really a system problem as opposed to a manufacturing problem or a DRAM manufacturer problem. Essentially, this is the conclusion. Manufacturer's retention time profile may not be accurate, so system has to do retention time profiling. And the paper that we wrote, we basically said there's no way of getting around this as far as we know without using error correcting codes. Meaning, if you really want to reduce the refresh rate, get rid of the 64 milliseconds, or basically figure out the retention time and do it by profiling, you need to rely on error correcting codes. Meaning, what does this mean? You reduce the refresh rate. If you're getting errors, that means that you're capturing the errors that happen for whatever reason, but usually the errors happen because of variable retention time, assuming you've done the data pattern dependence, you solved the data pattern dependence problem. And ECC helps you and it enables you to catch those errors in cases where the retention time dips significantly. But of course you need to have a strong enough error correcting codes in this case. And this paper actually, that's the future work followed that and develop mechanisms that can do this retention time profiling aggressively with ECC. So basically there's another very fundamental lesson over here. Essentially think about this variable retention time. You get random errors. Whenever you see random errors, you should always think about error correcting codes. Error correcting codes are very good at tolerating those random errors. Because there's no other way you can predict these errors. So you basically protect the memory with error correcting codes. And when the random error happens, hopefully the error correcting code is strong enough to catch it. If the error mechanism was not random, you could develop some other solutions. And we will see that when we talk about Rowhammer. If the error mechanism is very predictable, you can develop a customized, much simpler solution to the problem. And this is again an architect's mind. Don't solve the problem in a complex way if you don't need to. Random error complex. There's no other way to handle it, so you're going to do a heavy-handed solution like ECC. Why is ECC heavy-handed? Any guesses? Well, yes?
It requires a lot of extra memory.
Exactly. Basically, you don't know where these will happen, so you need to protect everything, right? So, yeah, and we will talk about ECC later on. Basically, you require extra memory. And if you want to become stronger, for example, there are some error codes that can detect single bit errors in 64 bits, and you may need 8 bits every 64 bits, right? That's the overhead is right now 12.5%. That's usually the case, actually. Usually single error correcting, double error detecting codes are about 12.5%. If you want to do more, if you want to be double error detecting, double bit error detecting, and maybe, no, what did I say? Yeah, double bit error detection, and let me get this right. Single error correcting, double error detecting, double error correcting, triple error detecting. Okay, usually codes don't work that way. You can correct one less error than you can detect. And SecDet is single error correcting, double error detecting. DecDet is double error correcting, triple error detecting. But of course, when you move from single error correction to double error correction, you get a lot more overhead. And the overhead keeps growing. So you need to be very careful in terms of how much ECC you add. And actually, this is not great in the end because you cannot use these ECC bits for something else. Of course, as an architect, you should always be thinking, can I use these bits for something else? Right? If you're not using it for a refresh, maybe you do it for something else, right? It turns out that's not an easy problem also to solve. Okay, you can see how rich this is, right? We're introducing now error correcting codes. Actually, now, it used to be that DRAM chips didn't have error correcting codes inside them. Now they have error correcting codes inside them, and this is the reason. Not for profiling yet, but the reason is really variable retention time. DRAM manufacturers figured out that it's very difficult for them to bound the minimum retention time of a given DRAM cell without having error correcting codes, because they need to do a lot of testing. And testing is not good for them because it takes time, which means that it eats away from their time to market, which essentially means money. Every single minute means money for them. And it affects their yield also. If they do not catch these errors, then some of the chips are not good, right? And they could be liable for very different reasons, of course. So they decided to add error correcting codes in recent DRAM chips. And all low power DRAM chips that you can buy in the field today actually have error correcting codes. Okay, so you can see how things are evolving right now, right? Okay, so of course, as I said, you need to keep the overhead of ECC in check in this case. Okay, and this is the study basically that we did. We published Radar, and we later said, can we make this work in real life? And then we built this infrastructure. It's an FPGA-based infrastructure that you will see. I should have copied these over here, but I didn't intend to spend this much time on refresh, but that's good. We're doing a lot of brainstorming. We built this FPGA-based infrastructure that can test DRAM, and that's how we actually figured out the retention time of different generations of DRAM chips. And if you read this paper, you'll see a lot of interesting analyses. But maybe I don't want to cover this right now at this point. Okay, basically the question now, once you understand the problems, the question now shifts to how can we reliably find the retention time of all DRAM cells? So there are multiple goals here. Once you have this information, so this is another question now, right? If you, for some reason, you want to find the retention time of all DRAM cells, what can you do with this information? You can make DRAM reliable and secure, and you can make techniques like Radar work. Because if you have this information as a manufacturer, you can make DRAM more reliable as well, even if you don't want to do Radar. So this is a good thing to do, independently of this particular idea that pushed us to develop this mechanism. So basically, you can improve performance and energy. Now, I'm not going to go through a lot of these works over here. This is just to give you an idea of how rich this field is right now. Basically, now the question is, how do you... There are different types of error correction mechanisms. ECC is one of them. Online profiling of errors is one of them. And there are a bunch of other ones. How do these works fare? And there's an experimental study that talks about it. I'm not going to cover this. We will cover it when we talk more about reliability. This is the state-of-the-art work that handles the variable retention time phenomenon. Basically, it uses ECC. It basically reduces the refresh rate for a DRAM cell or for a DRAM row, and if the ECC gives errors, then it increases the refresh rate, backs off basically. And you need to keep track of the refresh rate for all rows. So it's not going to be as efficient as Radar in the end. So there's room to improve this one. But this is at least reliable in the presence of VCC. And there's more work that handle the data pattern dependence, but you can take a look at these works if you're interested. I'm not going to cover them right now. And you can also actually, once you understand the data pattern dependence, for example, if you know the memory content, you can correlate that memory content with the refresh interval, right? So basically, you can keep track of the memory content of different memory rows, and you can guess what is your refresh interval should be. And if you don't write to the content, your refresh interval should be constant, minus the variable retention time effects, of course. That's the idea over here. For example, if all of your cells are 0, they're not charged, they're not going to leak, right? You don't need to refresh those cells. This is, of course, a very naive example, but that's the example. Okay, and this is one of the latest works that looks at a more basically, this retention time profiling turns out to be very hairy. There's a complex trade-off space. You need to basically find all of the cells that are going to fail, but you need to do it quickly, and you need to do it with less, as few false positives as possible. So whenever you profile, if you profile very aggressively, basically you need to ensure that you capture all of those cells that are going to fail, right? That's very important. That's called coverage. But also your profile may capture other cells that are not going to fail if you reduce the refresh interval, because you want to be very aggressive and find out many cells that are potentially failing. So if you find out those cells that are not going to fail, and if you find too many of them, then you're going to not have a lot of benefit by reducing the refresh, because you're thinking that they're going to fail, but they're not going to fail really. And also you want to do this quickly. So there's a complex trade-off space in terms of profiling, even in a deep concept like this. The question is, how do you enable fast and robust profiling? And this paper actually introduced a very nice idea, I think. The idea is, if you want to operate at a refresh interval, let's say, I don't know, to 256 milliseconds, profile the cells at 512 milliseconds, and find out the cells that fail at that point. And those will be a superset of the cells that are going to fail at 256 milliseconds. That's the idea. Basically, find that superset. If you want to operate at, let's say, 50 degrees Celsius, find those cells that are going to fail at 55 degrees Celsius. Those cells that fail at 55 degrees Celsius is a superset of those cells that are going to fail at 50 degrees Celsius. Now the question is, how do you determine that, well, the numbers that I gave you? What interval should you profile? What temperature should you profile at? So that you navigate this complex trade-off space nicely. Meaning you have 100% coverage, as close to 100% accuracy, meaning that you don't refresh things more often than needed, and at very low profiling overheads. Now the good thing about profiling at higher refresh intervals and temperatures is, if you profile at higher temperatures, basically you're reducing the time to profile, because at higher temperatures you're leaking more. And if you profile at a higher refresh interval, you're getting rid of a lot of the refresh intervals that you don't need to test, because you're trying to profile something higher only, right? Okay, so there's a lot of room for creativity, basically. Okay, so now this is profiling. Any other questions on profiling? We could go deeper actually over here, but I think for the purposes of this lecture, this is probably good enough. Any other ideas on what you can do for profiling? At this point, this is not a completely solved problem, let me put it that way. Even though there has been a lot of work in this area, and the overhead has been reduced significantly, it still needs to be solved. Okay, no other ideas yet. Okay, let's talk about binning. I think this is also fascinating, because if you do something simple, this can lead to a lot of overhead. Basically, this is the problem that the Radar paper solves actually. How do you efficiently and scalably store rows into retention time bins? And the idea, as I told you, is using hardware Bloom filters. Right? So what is this? What do I mean by efficiently? Efficiently means you don't need to store a lot of bits to determine the retention time of a given row. Scalably means something different. So I have a system, I have some amount of DRAM in it. If I increase the amount of DRAM in it by changing the chip, and you can do that in some systems, then the storage that I have in the memory controller should be able to support that, right? It should basically scale with the size of the DRAM chip that I can plug into the system. So meaning that if you have a single table that can store information for some number of rows, is not good enough if the number of rows increases once you add new DRAM chip, right? So that's a problem. That's a real problem that you need to deal with. That's why having a hard-sized table for some number of rows is not good. It's not efficient, but it's also not scalable. Okay, so some of you know about Bloom filters, so let me introduce the concept, because I think this is something that you can take away forever in your lives. It was introduced by Bloom, Burton Bloom, and this is essentially a probabilistic data structure to represent set membership. Basically what we're trying to do is we have this set of cells, set of rows, let's say, because everything is the row granularity, set of row addresses that need to be refreshed every 64 milliseconds, right? It's really a set. You want to represent the set with as few bits as possible. That's our goal. So the question is, how do you represent the set? You can have 1 bit per every row in the system that says, if it's set to 1, then you need to refresh it every 64 milliseconds. If it's set to 0, then you don't need to refresh it every 64 milliseconds. But that's not good, because that's basically exact set membership. 1 bit per any potential element in the set. That's exact membership. If I need to draw it over here, let's try to exercise this thing over here. Are we capturing this part, do you think? Even if we're capturing it, do we have something to write on it? Okay, I think we do. So there is actually one way. No, I have a way here. So there are multiple solutions. So basically you have a bunch of rows in DRAM. So I said 2 to the 23 rows, right? And I have 1 bit per row. This is for 1 bit. This is the 64 milliseconds bin. That's a lot of bits. This is 128 milliseconds bin. That's another set of bits. So this is representing exact set membership. Row 0, basically let's say it's 0, 0, meaning it can be refreshed every 256 milliseconds, right? You don't need to represent the 256 milliseconds because everything else can be refreshed every 256 milliseconds. Row 1, let's say if it's set to this one, basically it needs to be refreshed every 64 milliseconds. Row 2, let's say it's here. Basically you populate these tables. Essentially these are a lot of bits to represent this set exactly. Now you get exact information. You ask the question, should I refresh row 1068? You index these bits, find the bits that's corresponding to row 1068, check the value, let's say if it's 01. If it's 01, you need to refresh it every 128 milliseconds. You have that information, right? So whenever the memory controller generates an address to refresh, you check these bits. Now this is not very efficient because you're consulting a huge structure, first of all, and you're also storing a huge structure, but it's also not scalable. What if I increase the number of rows from 2 to the 23 to 2 to the 25, right? Well, you need to have additional bits over here, somehow. But if you didn't provision for that, then it's not good, basically. You cannot do it, essentially. You cannot use this technique if your memory size increases from here to here and you don't have enough storage for the bins. For the bins in this case. But this is exact set membership. Now what if we didn't want to be exact? We wanted to be approximate. Can we represent each of these more approximately? And that's the idea of a Bloom filter. Basically a Bloom filter takes this and compacts it to, let's say, I don't know, I'll pick a number, 256 bits. Right? Now basically you lose, clearly you cannot have a single bit per row in this case, but now you can actually use these 256 bits to store the addresses that you need to refresh every 64 milliseconds. So how do you do that? You need to represent these addresses somehow in this bit vector. So let's take a look at, I don't know, one address. So an address, let's say, I don't know how big it could be. Let's say 28 bits. I just made this up. And somehow you need to reduce it to a single bit. How do you do that? You go through a hash function. Meaning you pick some bits over here and, I don't know, XOR them, let's say. Well, I guess hash function could be an XOR function. Let's say I pick this bit, and this bit, and I XOR them. And for this address, for example, if it's all zeros, we get 0, right? Well, you could also AND them or them also, right? You could have different functions over here, right? So let's take, basically, this hash function determines which location you access over here. Basically, this is the address. And you reduce the address to an address in this 256-bit space. And now once you reduce the address, now this bit that has the hashed address represents the membership of this row address. Now if this row needs to be refreshed every 64 milliseconds, you set it to 1. If it needs to be refreshed every 128 milliseconds, let's say we have another bit vector. Again, that's much smaller than this one. Then you actually use another hash function for that, but that's fine. You set that bit that corresponds to this address. Make sense? Basically, you take the address and represent it with a single bit over here, and the representation is done by hashing the address to another address that is part of this address space. So for example, you determine that rows 5, 128, 2051, and 16,383, let's say, need to be refreshed every 64 milliseconds. You need to go through the same hash function, set the corresponding bits over here. Make sense? Now clearly, this row and this row may happen to map to the same bit now, right? That's possible because clearly you don't have 223 bits over here, now you have only 256 bits. You can have this called a hash collision. Hopefully you know about hash tables, right? You have a hash collision in this case. They map to the same bit. And even though one of them may need to be refreshed every 64 milliseconds and the other doesn't need to be, you set the bit, which means that the other one that doesn't need to be refreshed every 64 milliseconds is seen as having to be refreshed every 64 milliseconds by the memory controller. Right? That's the idea. This is a false positive now. And I will show you an example of the false positive in a pictorial way. Basically, an address seems like it's inserted to the set representation, even though it's not inserted. The bit that it maps to gets set by some other address that's inserted. Essentially, you get a false positive in that case. Now, in this case, false positive is not a problem, right? Because you set the bits for some rows whose bits should not really be set. Meaning that if you think about what this means from a refresh perspective, this row doesn't need to be refreshed every 64 milliseconds, but now it's going to get refreshed every 64 milliseconds because it maps to the same bit that maps to, that another row that needs to be refreshed every 64 milliseconds gets mapped to. Okay? So this is not a problem. You just need to issue some more refreshes than you really need. Now the good thing is there are no false negatives. Now what does that mean? Basically you don't set a bit when you're really supposed to set a bit. That doesn't happen in this case. Because your hash function sets the bit and you never remove that bit. There's no way of removing that bit. As a result, there are no false positives, and this is a fundamental characteristic of a Bloom filter. It can lead to false positives, but there are no false negatives. And if your problem, and this could be used, this data structure can clearly be used for many reasons, but if your problem can tolerate false positives, then this structure is a good structure. If your problem can not tolerate, well, false negatives are not a problem, so let's not talk about that. Okay, so that's the idea over here. Oh, wrong one. Now let's go through this a little bit more. So I think I already covered this. Basically, this is really a probabilistic data structure that compactly represents set membership, presence or absence of an element in a set. And I've already shown that non-approximate set membership is not efficient, but approximate set membership enables you to use a much smaller number of bits and indicate each element's presence or absence with a subset of the bits. I also said that some elements map to the bits that other elements map to, and there are multiple things that you can do to the structure. You can insert a bit, you can test whether a bit is set, or you can remove all elements. So let's take a look at this pictorially with an example. So I gave you one hash function, right? But setting only one bit in a bit vector to represent an address leads to a lot of false positives, it turns out. If you set multiple bits and check whether multiple bits are set to determine the presence of an address, it gives you more confidence. Basically, it reduces the false positive rate. So having 3 hash functions, for example, let's say we insert row 1, you don't set just one bit. You basically go through 3 different hash functions and set 3 different bits. And the presence of row 1 is determined by the fact that these 3 different bits are set. Now if some other row comes and sets this bit, it's not going to cause a false positive immediately because it's not going to set this bit, right? Basically these different rows get mapped to different bits. As a result, hopefully you reduce the false positives if you choose your hash functions nicely, of course. There's a lot of theory that goes into it also, which we're not going to cover clearly. So that's the beauty of this data structure. You can play tricks with the hash functions, you can play tricks with the size of this. So let's take a look at this example. So if you want to insert row 1, let's assume that row 1 needs to be inserted into the 64 millisecond bin. You go through these 3 hash functions and set these 3 bits. Now if you want to check the presence of row 1, the memory controller queries this data structure. Basically it goes to the same hash functions, and clearly it finds ones because we've inserted it, and you basically need to AND those bits that you get. Basically all of those need to be 1 for it to be present, and in this case it says yes. Now let's take a look at row 2. So if we insert only row 1, we're going to check whether row 2 is present. You go through the same hash functions. It turns out these 2 hash functions map to zeros. This 1 hash function maps to 1. Not a problem. We're ORing them, so you don't get a false positive. So you correctly decide that row 2 is not present. Okay, now let's take a look at another example. We basically insert row 4 in addition to row 1. So row 4 sets 3 other bits. It happens to set 3 other bits. It could map to the same bit, of course. Then in that case it's not going to reset, it's going to keep that set. But now we have 6 bits set. Now let's take a look at row, we test for row 5. Row 5 now maps to these 3 different hash functions, and it turns out they all lead to 1s. But we've never inserted row 5. The fact that we inserted row 1 and row 4 set 6 bits, and row 5 happened to collide with different bits that were set by the insertion of these 2 different rows. As a result, you get a false positive. Okay. So if you're interested in Bloom filters, this is the fundamental paper that introduced it. It has a lot of impact, clearly. And as I said, this is not a hardware data structure, it's not a software data structure, it's an all data structure. It's a data structure in the end. As I said yesterday, anything that can be done in software can be done in hardware and vice versa. And this is an example of this, right? So, and you can see actually, this is a very, very nice paper. You can see, for example, the terminology is a little bit different, but basically the computational factors considered are the size of the hash area, that's the bit vector space, the time required to identify a message as a non-member of the given set, reject time, and an allowable error frequency. And that's really the false positive in this case. It's called errors in this case. But then now you can actually, you're allowing errors. You can tolerate false positives in maybe modern terminology in this case. And I think it's nicely described over here. For example, in such applications, these are the applications that can tolerate these errors or false positives. It is envisaged that overall performance could be improved by using a smaller core resident hash area in conjunction with the new methods, and when necessary by using some secondary and perhaps time-consuming tests to cache the small fraction of errors associated with the new methods. Anyway, you can read the paper. And this is actually used whenever you have this sort of set membership representation, whenever you can tolerate false positives, you can use this. Whenever you're doing filtering of web pages, for example, Bloom filters are a very good example thing to use. Let's take a look at this one. So basically, clearly with any other idea that you have advantages and disadvantages. Clearly this enables storage efficient representation of set membership. Insertion and testing are fast. I didn't talk about that, but if you actually use a small bit vector, it's very fast to access, right? Compared to a 2 to 23 element bit vector. No false negatives. We said that if Bloom filter says an element is not present in the set, the elements must not have been inserted. There's a guarantee. And this enables trade-offs between time, storage efficiency, and false positive rate. By playing with the size of the storage bit vector and the hash functions, you can change this trade-off, essentially. And you'll see in the Radar paper, if you read it, that some of the different kinds of Bloom filters are examined. Of course, there are disadvantages. You get false positives. An element may be deemed to be present in the set by the Bloom filter, but may never have been inserted. And again, if your application tolerates this, it's not a problem. And the refresh is a good example. The application tolerates it, of course, but if you, let's assume that in the extreme case, all of the bits of the bit vector is set, right? Then you're not gaining any benefit from Radar, right? You basically are refreshing everything every 64 milliseconds. So that's not good. You don't want to be in that state. That's why sizing this is important and hash functions are important. Clearly not the right data structure when you cannot tolerate false positives. Okay, so I think I've already discussed this. We can tolerate false positives in this case. You can basically refreshing some rows more frequently than needed. No false negatives, so no correctness problems. It's scalable, so this is another advantage of a Bloom filter. A Bloom filter never overflows, unless it's a fixed site table. You keep inserting elements, you keep setting bits. In the worst case, you'll get 100% false positives. Right? And efficient because you don't need to store information on a per row basis in this case. And as a result, the paper has a structure that shows that you can have 1.25 kilobytes for a 32 gigabyte DRAM system with 2 filters. Okay, I think I already talked about this. Basically, in hardware, there are other use cases also. We're not going to talk about this one, but this is also another work that we've done, and it's a very completely different use case. Basically, this decides which blocks should be inserted into the cache, and it decides it based on it by using a Bloom filter. And the idea is actually I'll give you the idea. It's a very simple idea. If you recently evicted a block from the cache, insert the address to a Bloom filter. And if some other block, if you get a miss in the cache, check if the address is in the Bloom filter. If the address is in the Bloom filter, that means that you recently evicted a block that you really should not have evicted. Because that Bloom filter is a representation of the addresses that were evicted from the cache recently. Now you can treat that block differently because you know information about it. You recently evicted it, but you shouldn't have evicted it. So maybe it has high reuse. So you put it into the cache at a very high priority so that it doesn't get evicted. That's the idea over here. And that Bloom filter is the right structure again over there. Not as good as, actually Radar is a better application for a Bloom filter because there are some issues related to when do you clear the Bloom filter is a problem actually. In Radar you don't need to clear the Bloom filter unless your retention time profile changes significantly, for example. But then you're better off constructing a Bloom filter from scratch in that case, right? But in this case, it's a bit different because when do you clear the Bloom filter? When do you consider some eviction not recent anymore, right? And that becomes hairy because there's no way to remove an element from a Bloom filter without removing multiple elements. Unless you're lucky and you just happen to map to those bits that no other elements get mapped to. Okay, so basically refreshing is the third part. This is the easiest part, as I said. Basically you need to choose a refresh candidate row, determine which bin the row is in, and determine if refreshing is needed. And there's a controller structure that is written in the paper. It's very easy basically. You generate an address as a refresh candidate every 64 milliseconds, and you basically check whether you really should refresh the row at this time, or every other 64 milliseconds, or every 4th 64 milliseconds window. So you need to basically keep track of this. And this is very easy to do as long as you know what you're doing in hardware. Okay, so let's take a look at the baseline design. So refresh control, there are 2 options for Radar also. So now we've discussed the idea. Let's go into a little bit more implementation. Because to make it work, you need to really go into the implementation. Where do you put the logic? Do you put it here? Do you put it here? The paper talks about here, but there's another option which is putting it here. So in today's systems, refresh control is in DRAM. So what happens is you send a refresh command and memory control doesn't know which rows are being refreshed actually. Now Radar changes that. Radar questions that. Memory control should know which rows are being refreshed, and it can reduce them. So in either the controller you can do this or the DRAM can do it. Let's take a look at the controller. You can have it in the controller like this. In this case there's some overhead. But then there are also additional commands that are issued for per row refresh. This doesn't exist in current systems. As I said, in the current systems, memory controller periodically issues a refresh command. DRAM knows what it's refreshing, but memory controller has no idea which rows are being refreshed. It didn't used to be that way. Historically, the refresh was the responsibility of the memory controller, and then later people decided DRAM is better off doing it. And now it's not clear what is the right solution. So the solution that's discussed in the paper is this. But there is an alternative. The idea can be implemented also in DRAM by putting the logic inside the DRAM with a little bit more overhead, as you can see. But now the memory controller can still issue refresh commands once in a while, and the DRAM basically refreshes whatever as much as is needed. Of course, I think to be able to get the best out of Radar, it's better to have some better communication between the memory controller and DRAM, basically. The DRAM, for example, should tell the memory controller when the refresh is done so that the memory controller can go ahead and do other stuff. Anyway, we'll get back to this type of control later on, maybe. Okay, I've already given you the results. I'm not going to cover them again. Maybe let's brainstorm a little bit. I wanted to cover the course logistics also, but maybe that's not interesting. What do you think? Okay, I think we've discussed a lot of brainstorming here, so I want to preserve some time covering the course logistics. But think about this a bit more. What else can you do to reduce the impact of refresh? What else can you do if you know the retention time of rows? I think we've discussed this a lot. And we've discussed this a lot also. And this is going to be probably one of the recommended readings for your homework. Actually, you'll need to do some readings, and this is one of the things that you could select. Let me summarize the refresh part. Essentially, this is still a critical challenge for DRAM. Now, it's less of a challenge right now because there's been a lot of work in recent years. But it's still important, and creative solutions are still very much needed because you need to scale the DRAM technology efficiently to higher capacities. And we've discussed several solutions like eliminating unnecessary refreshes, reducing the refresh rate with online profiling and detecting and correcting errors. And this is something we did not discuss as much, but I'm going to flash the paper a little bit. Parallelizing refresh to the accesses. This doesn't get rid of refreshes, but this does get rid of some of the performance impact of the refreshes. And properties of retention time behavior is really important to understand in the end. And I think there are many avenues for overcoming DRAM refresh challenges. How do you handle these two phenomena is important. You developed a lot of ideas that could be useful. How do you enable online retention time profiling and error mitigation in different ways than what was explored before? And I think this is also very interesting, exploiting application behavior. So if an application, some of the ideas were discussed actually, if an application can tolerate some of the errors, maybe the issue is easier. There were some works that showed, for example, that neural networks can tolerate these errors, and you can actually determine your refresh rate based on the error tolerance of the neural network, and you can retrain the neural network such that you can still get high accuracies given some number of bit errors that you get when you reduce the refresh rate. Those are certainly possible things to do, especially if you know enough about your application, right? So there's a lot more you can do once you go and take advantage of the application behavior. And this is the paper that I mentioned that I was not going to talk about, and I'm not going to talk about that, I promise, right now, because we don't have a whole lot of time, I think. Okay. So I will end up with this. Basically, after we were starting doing work with refresh, we did a lot of work with Samsung also actually. But there's this paper that is going to pop up multiple times. This is written by two companies that don't talk to each other, Samsung and Intel. I don't think their lawyers even talk to each other as much. But they were nice enough to write this paper to the memory forum we organized in 2014. And they basically covered the difficulties they're having with increasing the DRAM technology to the future, is reducing the DRAM cell or scaling the DRAM process. And you can see the key problems, right? Two of them are related to retention time. Refresh is becoming worse, variable retention time is becoming worse. This is published after our papers were published. And I like the descriptions that they have. They also say write latencies are increasing, but I think this is less of a problem. But still, it's an important problem. There's a reason why these are increasing, because there's significant resistance between the cell capacitor and the access transistor. Anyway, you can read the paper. It's only a 4-page paper. You can take a look. And the solution direction that they propose is a solution direction that we've been following, which I think is a good direction. Basically, you don't try to solve the problems at one level, but you really partition the problem solution across different levels. Meaning, the controller becomes more intelligent to solve the problem. If you think about what you just discussed, essentially we're building a more intelligent controller that can handle a problem as fundamental as refresh more intelligently, right? As opposed to refreshing everything every 64 milliseconds, which probably many people would agree that it's not intelligent, right? Okay. So basically, we will dig deeper more in this course, and I think keep this in mind. I think Radar is a great idea, but really the difficulty is how do you make it work? And I think there's still more to be done to make ideas like this work. Okay, so that's the end of the memory refresh. Any questions? Should we take a 5-minute break before we talk about the course logistics? Let's get started. Before I move to course logistics, any other ideas on refresh? I think yes, please.
Really quick, the radar, like it's a physical thing that you have to implement onto the DRAM, right? It's not just in the software.
That's correct. It's something you either implement inside the DRAM chip or inside the memory controller.
So there are costs associated with it.
Absolutely, yes. And those costs are in the evaluation. If you read the paper, it's also said in the evaluation those additional costs are taken into account. And the Bloom filters, that's why it's really important to minimize the size of the Bloom filters and the storage that you need to keep track of which rows need to be refreshed how often. Especially inside a DRAM chip, actually. We will see later that putting something inside DRAM chip is very sensitive in terms of the area, because those chips are really optimized for packing as many bits as possible for storage. Any other questions? Now that I've discovered I have more time, I can spend some more time on questions and brainstorming. If I make this mistake again, please predict and let me know. I'm known to make this mistake, I think, for some reason. 3:30. Yes?
Can we change the hash function so that it doesn't have a lot of false negatives?
False positives, right? Yeah. Certainly, there's been a lot of research on that, actually, both theoretical and practical, in terms of how you should really construct the hash function that minimizes the collisions or false positives. I think in the paper we have some references. I think we use a particular hash function called H3. So there are names for these hash functions also, actually, and how you construct them. So Bloom filters, after they were introduced in 1970, they were applied in many different domains, and there's been a lot of work in that area. But still there's some art in terms of how many hash functions should you actually have, because there's overhead to hash functions also, because you're really doing computation with the hash functions, right? Well, at least bitwise computation on the address bits. They can get more sophisticated with hash functions. For example, one good hash function actually is to divide a value with a prime number. That gets you very good randomness in general, especially if it's a large enough prime number. But of course, doing that division is not easy. Another good hash function is really doing some multiplication with some. So you treat the elements of your address as a matrix, and you multiply with some other matrix, and that leads to a hash function. Of course, there's a lot of theory involved in terms of, actually a lot of theory gets involved in these hash functions that are randomizing. If you're interested there, I can point you to some references. But the paper's reference is a good start, and then you can trace back a lot of references. But the original, everything's really started with this Bloom filter paper. I would definitely recommend reading it. Even though the terminology is slightly different, once you overcome the terminology, I think you'll appreciate the value of the introduction of a data structure like that. Any other questions? Otherwise, I'll have to move to the boring part of the lecture, which is the course logistics. Okay, I think I already summarized this. I'd like to also point out, well, I think this paper will come up later on. I think I would also recommend reading this paper. But as you can see, this is the variable retention time phenomenon they depict, right? And our paper we actually analyze this phenomenon very heavily. And I think I'll go through the backup slides. So if you think memory refresh is just for DRAM, as I said earlier, think again. How many of you think that flash memory doesn't need to be refreshed? I think I answered this question already, but usually when I ask this question, everybody thinks flash memory doesn't need to be refreshed. What do you think? Do you need to refresh flash memory? The SSD? No? Yes?
You do. I think you do.
You do? Okay.
I feel like unless it's mechanical, it doesn't definitely have some sort of leakage.
Leakage? Okay, yeah, that's a good way of thinking, but maybe other people think you don't. Anybody else? it's non-volatile memory, right? Flash memory is considered non-volatile memory. It's a storage device. Okay, so I heard something, but I didn't get.
Does it depend on the type of flash memory?
It does depend on the type of flash memory. It does depend on how many times you've written to it. So it's very interesting. Maybe we'll have a lecture on flash memory. But basically, it turns out retention loss is one of the major problems with flash memory, especially after you've worn the device out a little bit. If you've written a lot to a flash cell, it becomes more and more leaky. And basically you lose charge over time. Very similar to DRAM, although it's not at the same time scale. The DRAM time scale is very fast, 64 milliseconds, let's say, although we deconstructed that as well. Flash time scale, initially you can refresh every 3 days or so. But if you're really pushing the lifetime of flash is measured by how many writes have you done to a cell. If you've written a lot to the flash, and the specification could be, let's say, you can write 5,000 times to a given cell, right? You normally exhaust it actually. Actually, a lot of flash devices, you really want to exhaust that and try to increase that boundary. So if you're actually close to that level, then you need to refresh flash more often. Let's say hours, on the order of hours or so. And in a lot of the data center SSDs, especially if they're subject to writes, the SSD controllers refresh flash memory today. Yes?
Is it a self-reinforcing loop so that it gets worse because it has to refresh more often? So does the refresh also?
That's a great question, basically. If you're interested in that, you can read that paper. And absolutely yes. Because refresh, you need to be very careful, basically, how you do the refresh. Because whenever you do the refresh, you're essentially writing to a cell. And the problem becomes worse when you write to the cell. So how do you actually ensure that that write doesn't cause worse retention time? So I'm not going to cover these papers, at least not right now, but this was a paper that talked a lot about refresh, a lot of real system data that we provided. But also this also looks at data retention and tries to provide other solutions to the problem. So it turns out, for example, even if you get errors in the SSD or flash memory, you can recover some of those errors if you understand the retention characteristics of different cells. Some cells leak data much faster than others, and you can use this information as an error correction mechanism to recover the data. And I'll let you think about how you can potentially do it. But this paper proposed a mechanism to do it. So if you really understand what's going on underneath, even though you may think that your drive got an error that is not correctable, wait for a while and let the data leak even more and figure out which cells are leaking at what rates, and use that as a probabilistic mechanism to guess what the values of the cells were before they leaked. That's the idea over here. Of course, this requires a lot of interesting implementation, and the paper talks about the implementation. It's called retention failure recovery. And data recovery is also important. So we've talked about data reliability. Reliability happens while the system, basically keeping the system reliable is important during online operation. But let's assume you've got an error. You don't need to quit at that point also. You can reconstruct what the data was with these mechanisms if you understand how the device looks like. Okay, I'm not going to cover more over here. Then we will not cover course logistics.